Okay, hello. Today we have Antti-Veikko Rosti from BBN. We're very pleased to have a topic on machine translation. Antti got his PhD from Cambridge under the supervision of Mark Gales, who is, of course, very well known in speech. Then he joined IBM in 2004, where he worked on speech-to-speech translation. And since 2005, he has been a scientist at BBN, working on lots of things: statistical signal processing, machine learning, with an emphasis on audio, speech, and language processing. Thank you.
Thank you. So today I will be talking about the machine translation combination work we've done at BBN for, well, mostly in terms of the Gale project. So here's the outline of my talk. So first I'll introduce the topic. I'll talk about confusion network decoding. I'll talk about confusion networks, not consensus networks. If you see those networks that come out of the MT hypothesis, you realize why I'm talking about confusion, not consensus. So there are a few things particular to machine translation hypothesis alignment, so-called skeleton selection, and then I'll talk about some particular improvements to it, and next I will talk about how we tune some weights for this combination. I'll show some experimental results and conclude the talk. So as an introduction, many of you know that system combination has been very successful in speech recognition since the work introducing rover and confusion network combination, and there is a tendency to build multiple systems in order to get a better combined output. Well, complementary is in parentheses because normally you just have various systems. You don't look at any particular, you don't measure the actual how much they are complementary, but there's been some work recently on that as well. And on machine translation, there are several paradigms: phrase-based, hierarchical, syntax-based, statistical side, and of course there's rule-based machine translation as well. And most of them have similar blue TR or media scores, but fairly different hypotheses. So we would like to leverage the information from each of these outputs. And it's the MT system combination is becoming more common in machine translation as well. If you look at the, if you had a chance to see some of the preliminary results of NIST MT08, you'll realize why, and soon they will be public in next month. And another reason why there's been some interest, growing interest in that, is several of these large-scale programs that involve multiple research groups rather independently developing their machine translation systems, like in Gale and TC Star, and we want to combine these systems. So we have actually studied 3 different approaches at BBN. We started at looking at some sort of hypothesis selection from the outputs, looking at the n-best lists from each of these systems. Then we also looked at phrase-level system combination, where we would redecode with a reduced phrase table that is only extracted from these machine translation outputs, or the outputs of the involved systems. And lastly, we looked at the confusion network decoding, which has been so far the most successful technique. So I will be only talking about this last one. So what is confusion network decoding? So given that we have, let's say, 3 hypotheses: cat sat the mat, and cat sitting on the mat, and hat on a mat. Here we have them aligned all nicely, and some nulls actually inserted there, and so we built this confusion network from this aligned hypotheses, putting a cat in the one word arc, hat in the other word arc, and as you see, all of the paths going through the lattice go through all the nodes. And there's, due to this second link, some people call these sausages, so I might call these sometimes as links and then the individual arcs as just word arcs. So in this second link we have 3 different alternatives, sat, null, and sitting. So we end up having 3 possible decoding outputs with the same number of votes. I'll come back to the issue of aligning the hypotheses and how we could possibly break these ties later on in this talk. So, as I mentioned, so there are the empty hypotheses may have very different word orders, so this alignment is a big problem. And also, there's something called skeleton. So the first hypothesis that is used in the, so this first hypothesis that is blue, it will actually define the word order of this final output from this confusion network. And since some empty systems are more reliable than others, and well, different inputs may differ from sentence to sentence, we might want to assign confidences to the words and assign weights to these systems. And since they are confusion networks, you can generate this kind of exponential amount of paths through this lattice, so you can generate almost a lot of nonsense sentences out of it. So we want to deweigh some of these ungrammatical outputs. So I'll first talk about hypothesis alignment. So there's been some work previously done. So the early work, 2001 ASRU paper by Bangalore et al. They used Levenstein alignment, so standard edit distance. Of course, it doesn't allow modeling of synonyms because some of the words may appear different but be synonymous, and it doesn't allow reordering. And also, it can be used in aligning incrementally. So this, they actually used multiple string alignment, some free packages from the biologist or bioinformatics sides. Then there's been some work on heuristic alignment as it's implemented in the media scoring by Jayaraman and Lavie, and it can allow matching of synonyms and even words with the same stem, but it's fairly heuristic, and it only allows pairwise alignment. So all the hypotheses have to be aligned to this skeleton pairwise. I will talk about that a little bit later. And also, Aachen, people at Aachen, Matsov et al. Have used GISA++ alignments, where they take the system outputs and consider all the pairs of these outputs as a parallel training data for training GISA models or HMM and IBM3 models. And this potentially can model synonyms and of course can model reordering. And one drawback is that the quality depends on the tested, so the tested size is actually a factor in there. And it can only be used in pairwise alignment. And something we have looked at BBN, or in the Agile team. So the first paper there is Kei Sim and Bill Byrne's paper about using the TR alignments in the confusion network decoding for machine translation. It doesn't model synonyms, but it allows reordering. It's simple and it's tested independent, and as I later on, so we can actually do incremental alignment on those as well.
Sorry? There's no obstacle to modeling synonymy that way, right?
Well, it requires work. We have tried some kind of hybrid TR meteor type of alignments, but we don't have any good results on that yet. So it's under research still.
When you say no good results, is that because it's hard to actually find the search problem of finding the best alignment is hard, or because you think that the synonyms will not actually improve the alignments that you get?
I don't know whether that is the case. We only looked at the actual decoding outputs. We had this alignment method called semantic TR. There was a recent ASRU paper about that. We tried that aligning the lattices. When you look at the lattices, they seem to have nice alignments and nice alternatives there, but the overall results haven't been encouraging so far. I mean, we obviously want to look into that further detail later on.
Another quick question. In the Matusov paper, you said they use Giza++, but I would think that is it as if they treat it as training data, or are the models trained on something else and then they just
No, they just take the outputs from each of these systems,
right,
and they put them pairwise. So output from system 1, output from system 2, then output from system 1, output from system 3, and so on. So you get, like, if you have n systems, you get n times tested size.
And then they treat these pairs as if it were a string of
As it was a string of parallel training data from English to English, and they train these models. They add some lexicons there, if I remember correctly, but that's practically how they do it.
And the reason that they and people working on this problem in general are trying to do the alignment post hoc is because most translation systems don't tell you what source words their translations came from.
Yes, it's for some of the systems. I mean, we use the alignments to the source in this phrase level approach that I briefly mentioned about, but we had some problems really. I mean, how to define it, because none of those were word-to-word alignments to begin with, and then when you have hierarchical systems, the phrases are. It's not even phrase-to-phrase alignment either. If there's no more questions, I'll talk about the alignment methods that we've considered so far. So this is an example of pairwise alignment using TR. And the idea is to, in this case, we have a let's say skeleton again. I'll talk about skeleton later more. This darker blue one, I like balloons, is the skeleton, and we have two other hypotheses. I like big blue balloons, and I like blue kites. And they are aligned with this skeleton independently, so independently of the other hypotheses, and we're using TR. So in first case, the alignment might be, I like big and blue as insertions balloons, and those nulls I've added there just for the final confusion network building. And in the second case, I like balloons, possibly balloons and blue get aligned together, and kite is an insertion. Of course, this is a toy problem and just an example, and it's not necessarily what comes out of it. And when you combine these two alignments into a lattice, into a confusion network, you would get I from all three outputs, like from all as well, and then the big blue would align with null from the third hypothesis and the skeleton, and balloons and blue will end up being in the same link there as well, and kites in the final link against two nulls. And that is how you could merge these two alignments. And of course, the problem is how to deal with these multiple insertions like big blue. One way is to just put them into one arc and consider it as a phrase. Or you could go and, if you have several multiple alignment, multiple insertions from several hypotheses, you might do some sort of alignment of these extra insertions there as well. But I mean, it's getting pretty complicated in that case, because then the skeleton doesn't have those words. It becomes pretty tricky, and it doesn't depend on the order which you align these things against the skeleton. Whereas the incremental alignment, we build initial word graph from the skeleton. So I like balloons. The first confusion network would have just I like and balloons. Then we align the second hypothesis, I like big blue balloons. We get two new links here with the big and blue and nulls from the skeleton. And then when we align the last one, we can align the I like with the I like from earlier, and blue with the blue from the second hypothesis. And kites will possibly be aligned with the balloons as a substitution. So the good thing about it is that it will take care of these multiple insertions with respect to the network, or it will generate new links for those, and it will allow the same words from the following hypotheses to be aligned to those as well. And it's fairly similar to multiple string alignment, apart from allowing shifts because we're using TR. Of course, I'm not showing in this example the actual reorderings, but this alignment algorithm we have implemented actually allows those block shifts just like TR does. But as a downside, there is it is order dependent, so it depends on the order in which we align these hypotheses into the skeleton. So far, we have tried few things to figure out which is the best order to align the things. And we tried at sentence level taking TR between this, all these hypotheses against the skeleton and starting from the lowest TR first. And that actually anything we've tried so far hasn't given us as good result as just using arbitrary set global order so far.
Question. So the alignment metrics that you talked about, either Giza or TER or Levenstein, they're all defined pairwise. In other words, it's between one string and another.
That's right.
So in incremental alignments, you need to extend that idea to one string and a group of aligned strings.
So you align string against the current confusion network.
Right. So is it obvious how to extend it? I mean, what is the cost of? In other words, in this case, for example, blue matching with big. So let's say the first two have been aligned, and you're aligning the third string. So in this case, it's obvious that the cost of aligning the green blue with the blue versus the green blue with the blue big. This one's the better one. But imagine now if I had something more complex, if I had another link in the middle with both being blue.
I know. There are various cases where you can still end up having similar words in two different places, depending on the order which they are actually aligned and depending on the outputs. I don't have any specific examples from real lattices. They would be ugly, I have to say.
Can you tell us what you did? I mean, did you do incremental alignment or?
Yes, I have results on both, and we have been using incremental alignment for the retest. Okay, retest actually.
Okay, I'll ask you offline what you actually do.
You said it's hard to make it better. Is it at least easy to make it worse in expected ways? So if you start with the highest TER as your skeleton, is that expected?
That makes it as well worse, but it doesn't seem to be much worse than using it from the lowest TER.
So it's really the same result.
That's right. That's right.
But since the word order doesn't change once you lay down your skeleton, everything has to be aligned with respect to that. So you have to choose as your skeleton the system which outputs the best word order, no matter what words it outputs.
That's right. Which is something I'm going to talk about next. So the skeleton selection. So the confusion network skeleton, as came up, is defining the output of the final, or the order of the final output. And so there's been some work. Things that we've tried is just using a best system on a development set. We used, even looking at after the fact, so using all of the systems as possible skeletons and then looking at which system gave us the best TRs and some other developments. And secondly, like Gage Isim and Bill Byrne surprisingly proposed was to use minimum base risk. So you align all of the hypotheses against each of these skeleton candidates, and just pick the skeleton that has the lowest average, the lowest average TR score, for instance. Or you can use any other loss measures there.
You said you align each of the sentences against each of the skeleton candidates. Does that mean that not all the sentences are skeleton candidates?
Well,
you identify some subset.
Yeah, if you're looking at combining one best outputs, for instance, you consider all the hypotheses as possible skeletons. You align all the you compute the TR between all the other hypotheses using the skeleton candidate as the reference. So you get and you take the average of those, and you pick up the one that has the lowest expected TR score as the skeleton. Yeah.
Sure.
So I'll show some results on those experiments later on as well. And there's the late decision that was proposed by Matsov et al. In their paper. So they built this. So they built a confusion network using all the system outputs as possible skeletons, and they combine it into one big lattice, which looks something like this one. So you have skeleton confusion network built around skeleton from the first system, another one from using the skeleton from the second system, and taking the skeleton from the third system. And you combine them into this big lattice. And what we have used is actually something similar to that. So we built this lattice, but we also estimate some prior probabilities for these first arcs based on this average loss estimated with the same kind of average TR out there. So it practically, gives in this case, gives a higher likelihood for this network. But if the network is completely giving some likelihood that is not as well, it's clearly worse than one of these ones with the lower prior, it can override the prior in the end. And we also actually, when I talk about system weights, we actually also multiply these priors with the system weights. So the system weights will actually also influence the skeleton selection. So how we assign the scores for all these hypotheses generated from these confusion networks. So we have actually considered taking 10 best lists from each of these systems. But since the TR alignment or the incremental alignment, or whichever one we're using, is fairly costly process, so we only consider the first the one best hypothesis from each system as a possible skeleton. And this is a fairly complicated way that we assign these confidence scores for the different words, but each time we align a word into this confusion network, each word arc has a vector of scores for each element representing each system, and we increment that score by 1 over 1 plus rank, where the rank is the rank of that hypothesis it's coming from. Well, that's an ad hoc thing that we found out that works, at least on some testers. And after the alignment process, these scores may be, if it's a 10 best, it may be up to 2.8 or something, between 0 and 2.8 for each of these systems and each of the words. We go and actually scale these system-specific word confidences into posterior probabilities. So within one of these links, all the possible word candidates, if you sum over the system-specific scores, they should sum to 1. I will show an example on the next slide about that. And the total word posterior then will be, if we introduce the system weights, will be a weighted sum of the system-specific word posteriors. And the hypothesis through this confusion network will be assigned a score that is a sum of these log of the word posteriors along the path plus any sentence specific features or features like the language model score, number of words, and number of nulls. Yes.
Are these features all on the arcs, or do you then extract a bunch of full paths and compute features?
These ones are actually on the arcs. I will tell you, show some of these over here. So here's an example of one of the confusion network links. So between two consecutive nodes I and I plus 1. and up to aligning one best hypothesis from, let's say, 9 systems in this case. So 9 systems, you have 9 confidence or nine posteriors for both of the words. So one word is null and one word is decided. And you also will have, in this case, there's no language model scores yet, so you have a placeholder for language model score. You have a score whether it's a word or null, and so when you find this path through it, those will be accumulated into the number of nulls and number of words along that path. And so in this case, the system 1, 2, and 5 have actually didn't have anything aligning into this particular confusion network link, whereas systems 3, 4, and 6, 7, 8, 9 had a word decided that aligned into this particular link. So that's so the scaling. So these after the alignment, these would all have 1/2 because it was 1/1 plus rank and all are one best hypothesis. But they will be always scaled so that these scores. So if you put these confidence scores into one matrix, all the columns will sum to 1. And the final log probability for the hypothesis, as I said, is there's the weighted sum of the system weights and these posteriors, and we take the logarithm. So over L goes over the number of systems, and we take logarithm of these posterior estimates and sum them over the path. Nj is the number of nodes, and there's always nj minus 1 words including nulls in that particular hypothesis. And then we have language model score for that hypothesis, number of nulls, number of words. And each of these have weights, mu, and he there. And the system weights are lambdas. So there's 9, in this example, 9 system weights, of course, means 8 free parameters because the system weights are actually restricted to sum to 1. And
how many arcs do you have in which bin on average from your experiments? About 20, 30?
Well, usually not that many.
Okay. I mean, you have 9 systems times 10 because you have 10 best from the system. So you have at most 90.
At most.
Okay, but you usually have 10.
Usually they align better than that.
Oh, okay.
So there will be a few words in each link, few word arcs. And these weights, including lambdas, language model now, and word insertion penalties, well, the weights can be automatically tuned and jointly actually. And that's what, and the way we've done it this far is using Bubbles method on n-best lists. So the earliest reference on this same method is from Mary back in 1991 when they were combining the stochastic segment models with HMMs in Boston with BBN and Boston University. And the idea is to have, you have some scoring function, which in our case is this function here. It's a function of some features like the word posteriors and the language model and number of nulls and so on, and the weights. And the one best hypothesis is always given the one that has the highest score, and from all these one best hypotheses, you can get a test set output. You can compute TR against the set of references, and the idea is to find the set of parameters that minimizes, for instance, TR or blue or meteor or some combination of those measures. A few things. So the people working on machine translation probably recognized this method from Franz Och's 2003 paper, where he did minimum error rate training for I think it was a phrasal system for the decoder weights. And since that decoder was using a log linear model, he came up with this exact line match, some improvement to this bubbles method. But since our scoring function is not only a linear combination of log linear model due to these system weights, we just use the standard grid-based line optimization as it is just straight out of numerical recipes actually. And some implementation issues, so we generate n-best lists from this confusion network, and we can pre-compute all the score statistics, whether it's TR, Blue, or Meteor. And because they always, you accumulate the statistics for the one best and just compute the score from that. We can start from these some initial weights and do just for finding better weights, we do 19 additional random permutations of these weights as initial weights for the Powell's method. And so there's always kind of 20 different jobs running parallel, finding different weights, and then just a comment. So if you have 1,500 sentences or segments with 300 hypotheses each, it takes just over an hour in case of combining 9 systems. And it actually tries, so each of these 20 jobs actually tries about 1,000 or so, up to 2,000 different sets of weights in the algorithm. So it will end up trying quite a few different combinations of the weights. And the actual way we do it is that we first generate 300 best list, use some initial weights, which are usually uniform in the beginning. We go get 300 best from the confusion network, tune the weights, all these 20 jobs. We could pick the one that has the best objective function score, or the TR, Blue, or Meteor score. And then we go back to the confusion network, generate another 300 best list. We merge this new 300 best list with the earlier one, so that we get just to make the tuning more stable, and set off another 20 tuning jobs using these the weights from the previous iteration as the initial weights. And we do that actually 3 times, and we found out that after 3 times there's not much. The new 300 best list doesn't have many new hypotheses compared to the earlier or the previous merged n-best list. And the weights seem to be, and the scores seem to be converging fairly well after just 3 iterations. So finally, after we get these, let's call them decoding weights during these 3 iterations, we generate another 300 best list. We score that 300 best list with a higher order language model and train a new set of weights. So we have 2 sets of weights that we use in the testing situation. So for the test set, we use the decoding weights to extract 300 best lists from the lattice, and then we rescore the hypotheses and use the rescoring weights to reorder just pick the one best out of the 300.
Your objective function was to minimize. Your objective was to minimize the DR and the order blue.
Well, we talk about it next.
Okay.
So, as many of you know, the official metric for Gale is something called human-mediated translation edit rate. And so it's practically a TR between the hypothesis and the targeted reference. So the targeted reference is generated manually by post editors, looking at the output and making some edits so as to make the output, after this edit, the output should have the same meaning as this golden reference and be fluent English. Well, that's debatable, but But anyway, so after that, it's the TER between the hypothesis and targeted reference. And it's, as you know, it's a very, as you might guess, it's a really labor-intensive process, and it's highly, there's huge amount of variance there. So we can't really use that in the automatic tuning that I described earlier. So we have, carried out some studies figuring out which scores, which automatic scores correlate well with these HTR scores. And it was found that TR and meteor correlate best from these automatic metrics. Well, best is, of course, relative term, something like 0.3 and so on. But anyways, and some observations that I found out is that the hypotheses after the TR tuning tend to be shorter than the reference. So it seems to delete a lot of words there. Whereas if we tune for the meteor score, especially for the versions before 0.6, we tend to get something like almost 20% longer outputs than the reference. And so in those cases, we get something like 10 to 15 points worse TR scores or blue scores, and we weren't really happy about that. And actually, the version 0.6 has some weights changes in the actual meteor score computation, and it gives a little bit more reasonable lengths, but it's still around 5 to 6 points, TR points and blue points worse than if we use something, some more reasonable tuning criterion. And that's another observation. The hypothesis after the blue tuning seemed to be close to the shortest reference. Well, if you have multiple references, it's closer to the shortest reference length. We actually observed during the NIST MTO-8 when we were tuning our system for the normal machine translation systems for the NIST MTO-8, we observed that blue is really sensitive to the reference length used in the tuning, which might be different than the reference length in the testing. So there's questions.
Oh.
You.
I already asked one, sorry. All right, so was that because you were using in the tuning the shortest reference length to compute the brevity penalty? Or does that happen irregardless of the particular definition of brevity penalty that you use?
Yeah, I mean, that is NIST 4, that is the official metric for MT.
Right, but did you find that if you changed, did you run experiments using different definitions of?
Well,
Well, I mean, no. I mean, well, there are three standard definitions of brevity.
There is IBM Blue as well.
Right.
I think IBM Blue uses average reference.
Average, I think, and then there's close. I think Philip Kern proposes using closest.
That's right. Okay. Yeah. I mean, there are various ways. I mean, one way we dealt with that is that we used actually MTO2 to MTO5 as tuning data, and we tested on MTO6 newswire newsgroup plots. And we found out that if we use only those MTO2 to MTO5 in tuning, we actually get pretty bad brevity penalties for the MTO6. So apparently MTO6 references are longer than the references for the shortest references, longer than the shortest reference on the earlier MT evaluation sets. So we actually ended up using some newsgroup tuning data with single reference. It's obviously, if you have one reference, it will tune pretty much to that length, and by using some newsgroup data in the tuning, we actually improved even the newswire scores on the MTO6. But of course, there's many other ways of dealing with that issue. But it is an issue because we don't know what the references are going to be in the next evaluation. So if we measured on NIST 4, So it's always a gamble whether you tune for the shorter or a little bit longer, and you either get a hit by the precision or the probability penalty.
Okay. So, well, okay, so that's very interesting about the throwing in the newsgroup data. I mean, what I was going to ask even before you said that is, well, it sounds like an overtraining problem. As you said, you're doing okay on the dev set, and then you test, and it's worse. And so you throw in some data that are farther away from that dev set, and so your parameters are going to be smoother. So would that be another thing to try, perhaps? Some sort of
Could
smoothing
be other
or
thing,
prior.
but yeah. I mean, usually the over tuning when you're tuning just 12 weights or so.
I think it can still happen.
It can happen, especially if you. But it's a matter of also whether you have representative tuning set as well. And
but the fact that the newsgroup helped, at least to me, suggests that maybe that is the problem.
That's right. Yeah. So, I mean, of course, this raises the question: what do we optimize for the scale systems? And we actually found out, well, we don't want to hurt any of these scores. We don't want to hurt TIA, we don't want to hurt Blue, we don't want to hurt Meteor, even though we don't want to tune for Meteor either. So, well, of course, we've also noticed that it depends on the language pair and genre and number of references, which one is the, which we think is the best tuning metric. So especially, if we tune for TIA on Arabic, the Blue score is reasonable. If we tune for TIA on Chinese, the Blue score goes down a lot. So it depends a lot on the language pair and the genre as well. I mean, it's probably in the case of Gale, it's more like the number of references, because only some of the newswire sets we have 4 references, and most of the other sets we have only single references. So of course we're still looking for the better alternatives, but what we've used so far mostly is just half TIA plus half 1 minus Blue. And that's because that way we get good TIA scores, good Blue scores. I mean, if we actually end up having lower Blue score than some of the ISI systems, I think Kevin would come and kill us. But anyways, so that's why we want to balance them, all of them. So I'll show some experiments. So these are actually our P2 Arabic newswire output. So we had 5 phrase-based systems. Some of them were very different. Some of them were just variations of the same system, after like MBR similar things. There were 2 hierarchical systems, 1 syntax-based system, and we actually threw in 1 rule-based system as well. It's brought some interesting other issues there, as I'll describe later. And as tuning and test sets, we used, we put together NIST MT04, MT05, Gale 06, or the phase 1 evaluation data, and this set called Dev 08, and we split that into 2 disjoint subsets, as 1 for tuning, 1 for test. So the tuning set was around 1,500 segments, and the test set was under 500. And the combination was tuned to minimize TIA plus 1 minus Blue. Actually, for the audio sets, we usually used a little bit higher weight for the 1 minus Blue there. So just came up with some number that gave us good scores on the, or reasonable scores on the development test sets. And I will show some results on the B2 sets as well. So here's just what happens with the combining the 1 best outputs without any tuning and system weight. So these are the tuning set scores. And here you see the worst scores. They actually happen to be coming from the same system for TIA, Blue, and Meteor. So these are actually the rule-based system scores. So the rule-based system doesn't seem to give us very good scores, automatic scores, TIA, Blue, and Meteor scores, but it still seems to be fairly relevant after the weights tuning later on. And leaving it out would hurt the final combination. whereas the best scores, these are not coming from the same system. I just put the best TER score from one system, from the system that has the best TER score, and the blue score from the system that has the highest blue score. And if we use just a single system as the skeleton, so let's say best skeleton after the fact, so we built 9 confusion networks, and just vote from these. Well, it's practically voting because there's no system weights and no language model. We get these scores on this row here, and so if we use the MBR skeleton selection there, so for each sentence we choose based on the MBR criteria and which system we should use as the skeleton, we get fairly good improvements there. So especially on blue. So those blue score improvement is really significant, and I believe the TER score improvement is also significant. We've done some bootstrapping experiments to figure out the significance of these differences. And just as a reference, I put the one best oracle, so that if we choose the outputs that have the lowest TER sentence by sentence, so the best possible hypothesis selection would give us even better system. So there's still long way to go even to that one from these ones. And if we would have the best possible oracle, best possible skeleton selection scheme, we could get fairly good improvements as well. Unfortunately, well, since these are oracles and the actual distribution of these best skeletons is fairly flat, it may be almost as difficult as hypothesis selection of finding that oracle there.
Before you go ahead, let me make sure I summarize the slide correctly. So in this setting, there are 9 systems, each produces one hypothesis. Then either you choose one of them as your skeleton based on whichever was best on Newswire. Mm-hmm. And then
so these are coming from one system.
Right, and then you align everything incrementally to it, and then you rescore it, and there are no system-specific weights.
But there's no rescoring either. So this is just.
Oh, no LM either. Okay.
Yeah.
Okay. Just based on the counts, you pick up the best.
So this is the just voting. Just
voting.
Just voting. So just voting gives us fairly good scores over the the best scores there. So, well, I mean, blue score doesn't improve much, and the TER score probably improves because it's a TER alignment or some.
So just counting gives you a little bit.
Yeah, especially in terms of TER. So next,
there's a question.
Yeah.
So when you do MBR skeleton, do you do it sentence by sentence?
Sentence by sentence.
So I'm confused about the oracle skeleton with the MBR skeleton. Can you explain?
So the oracle is as well. If we generate a confusion network using each of these systems as skeletons, we have 9 different confusion networks. If we vote from each of these, and after the voting, go and look at the outputs that have lowest TER scores, we pick up the best one. So if we had a perfect predictor for the oracle, it seems to be lots better than the MBR. But I think MBR, I mean, we tried some other predictors using some other features, not just the TER, don't seem to be doing much better than the MBR, or reasonably better than the MBR.
So, but the oracle is still one of the 9.
Yes, it's just using one of the 9 systems skeleton. So there is no multiple skeletons, so none of those big lattices on this slide. The next slide will have those. So these are still the tuning set scores, but now we have 1 best and even 10 best outputs and system weights, bigram expansion, and 5-gram rescoring. And I have scores from the MBR skeleton selection, and then using multiple skeletons. So if I just built that joint lattice from all of the confusion networks, and what comes out of it after combining one best only in this case. So there's already we get fairly good improvement over the previous slide. There was MBR was 40.5, and here is 39.35. So 0.7 TR improvement, and what do we get? We get 49, and so we get 2.5 points blue gain, but that's mostly coming from the language model, of course, and all the other bits there as well. And so if we use these multiple skeletons, then we get, well, this is not statistically significant difference in the TR scores, but there seems to be a 0.4 improvement on the blue scores. The meteor score goes down by 0.05, but that's not significant either. And then I have comparison between combining 10 best systems using the pairwise alignment and the incremental alignment. So these use both incremental alignment there. So actually comparing this to this is using one best, combining one best and 10 bests. This is a fair comparison. Whereas comparing these is just aligning 10 bests, but using incremental instead of pairwise alignment. And here we see that the incremental alignment gives us 0.6 TR and gives fairly good around 0.8 blue score improvement, and that's actually statistically significant. And here the oracle skeleton is oracle from this after these expansions and all that. So this oracle is getting very close to the one best oracle. So where the one best oracle doesn't do any mixing and matching between different systems. So just quickly to the test set results. For the test sets, we have similar patterns here. So the MPR skeleton gives us fairly good gains over the even blue gains over the best individual system, and then there's some gains from the multiple skeletons combining one best outputs. And there's the improvement from going from pairwise to incremental alignment seem to be, well, that's almost 0.95 blue there, and it seems even better than the tuning set. And there's a sizable gain on the TER scores as well. And these are actually for those, well, I mean, these are the automatic scores for our E2 Arabic eval set output, and same things seem to hold here. One difference is that actually on this eval set, using 10 best hypothesis gives slightly lower blue score and very little higher TER score than using one best outputs there. So whether you're using one best or 10 bests in this combination, it's debatable. The benefits are debatable. But as on the earlier sets, the pairwise or the incremental alignment gives good improvements over the pairwise alignment, and there's a little bit of improvement from the going from the MBR skeleton to the multiple skeleton in terms of blue. I mean, these TR scores are practically the same.
So the summary seems to be to use multiple skeletons, use incremental alignment, and then use 10 best in that order. Means so the single most important thing is to use, which is more important?
Well, the incremental alignment seems to be the
So use incremental alignment whether you use one or multiple skeletons. Use multiple skeletons if you can, and use 10 best if you can.
Yeah, I mean, it's just a matter of computation then in the end. So
the first thing to do if I had to do something would be to do incremental alignment on whatever I choose as my skeleton and however of the n best I have.
Well, that may be a conclusion from these tables at least. I mean, of course, they may change from tested to tested, depending on the involved individual systems and all that. So actually, this concludes my talk. So
what about the result for Chinese?
I don't have results on Chinese here. But we actually, from the incremental alignment, we got a little bit higher improvement on Chinese, and otherwise pretty much the same.
By system combination Chinese?
Pardon me?
I mean, so on average you get more than 2 points per improvement, right?
Yes, I mean,
General.
yeah,
But on Chinese,
it's
can you
not
get the
quite
same
as big. Well, it's more than 2 points, but I can't remember the numbers of my head right now. But yeah, there's a good blue improvement as well. But I have a suspicion it's not quite as good as that because there's only one system that. Oh, well, actually, for the readers there were 2 systems that are doing really well. So the ISI syntax based and now our hierarchical dependency. Dependency-based system.
Do you have some sense of what role the diversity of systems played in these results? Or did you do like an ablation experiment where you remove systems and see what happens to these scores?
Yeah, I mean, on RRP, removing any one of the systems will have a small hit always on all of the scores. Chinese, removing the systems, some of the systems had actually positive effect as well, and even on Arabic, in these ones, some of the system weights are very close to 0. But even though they're close to 0, it doesn't mean.
I mean, if you assign the system weights.
Well, that's right. That's right.
Fine.
Yeah, well, at least we can say that we combined them. Well, I mean, sure. I mean, it maybe. I mean, we did the same thing with pairwise alignments earlier, and if you use pairwise alignments, dropping systems seems to be even on Chinese seem to be bad. But with the incremental alignment, it may be just that using that particular order which we aligned these hypotheses just didn't favor some of these systems, or well, which way you want to put it. But yeah, I mean, there's well, we usually want to combine all the systems, but of course, if there's I mean, none of the systems actually. Removing any of these systems doesn't make a huge difference in the scores. So you can't like gain 2 points by throwing all the phrase-based systems out. That would hurt us actually. Even on Chinese. So some phrase-based systems, even though their scores are not as good as some of the hierarchical and syntax-based systems, they still help. So conclusions again. So incremental GR alignment is probably the most important thing. Probably the second most important thing is, of course, the language models. No, it's probably the most important, actually, in terms of blue scores especially. So the language models, you use bigram expansion, you can use trigram as long as, but you would have to use more pruning in the language model expansion, just because there's a huge number of paths through the lattice. And well, of course, important thing is the joint optimization of all these weights at the same time. And we can good improvements, and for the future work, look at the hypothesis alignment still, maybe the order still isn't optimal, improve the skeleton selection, there still might be some way to improve it. And the work confidences are still pretty ad hoc. We might want to try something more more sophisticated there, and if we can find some way to tune for the HDL, it would be great before the end of the project or program. And there's actually some things about the incremental alignment. Since blue scores are computed if you have multiple references, they kind of mix and match the n-grams from all of the references. So the incremental alignment might be used to, for instance, align all the references into each other and then compute the TR against that confusion network. So you would use kind of all the words from the four references in the TR computation. It might be better metric, but we're still looking into that. So that concluded the talk. Thank you very much. I'm willing to take more questions. Thank you.